Have you ever wondered what music actually looks like? I don't mean the notes on a page, but the deep underlying shape of the sound itself. It's a question that honestly could completely change the way you hear your favorite songs.
Okay, so let's just dive right into this. For pretty much all of human history, we've had one main way of picturing music. But what if that picture is, well, incomplete? What if there's a hidden geometry, this beautiful architecture, just sitting right behind the notes we hear?
Think about it. A musical score, or even the timeline in your music app. It's a line, right? Time moves left to right, pitch goes up and down. Super simple, super effective, but it's also kind of flat. It's treating music like it's only a two-dimensional thing.
And it's a question people are definitely asking. Someone online put it perfectly. By focusing so much on that timeline, we might be losing sight of all the rich relationships between the notes and the chords, the very things that give music its emotional punch.
That really is the big question, isn't it? We're missing the depth, the symmetry, the transformations. We're missing the geometry. And by exploring it, we can uncover this whole new dimension to the music we thought we knew so well.
So, this idea, this connection between music and math, it's not new at all. In fact, it's an ancient obsession. It's this long search for the hidden numerical truth inside the art of sound. And this quest, it spans millennia. It starts way back with the ancient Greeks. You had Pythagoras, who discovered that the harmonies that sound so pleasing to our ears, they actually correspond to simple mathematical ratios. I mean, that was so profound that Plato and Aristotle made music one of the four pillars of math education, right alongside arithmetic and geometry. And that thread, it just keeps on going all the way through the Enlightenment and right up to today, where theorists are using these incredibly powerful geometric tools to visualize music in ways the ancients could only have dreamed of.
The great mathematician Gottfried Leibniz, he just captured this intuition perfectly. He was basically saying that when we're moved by music, our minds are unconsciously doing math, sensing this deep numerical order that we can't quite put our finger on.
All right, so to find this hidden geometry, we have to start with the absolute basics, the fundamental building block of all music. We're talking about the shape of a single note.
So, what even is sound physically? Well, it's a vibration. Every single sound you hear, from a whisper to a huge symphony, it's really just a wave of pressure moving through the air and vibrating your eardrum. It literally has a physical shape.
Now take a look at the shape of a pure, single note. It's a perfect sine wave. It's smooth, it's repeating, it's elegant. Every complex sound in the entire universe is just a combination of these simple waves. This right here, this is the very first step to truly seeing sound. A single point of light, a single perfect shape.
But music isn't just about single notes, right? It's about how they combine to form chords, and how those chords connect to tell a story. And this is where the geometry gets really cool. A linear score shows us that a C major chord is followed by an A minor. Okay, fine, but it doesn't really show us how they're related, or why that switch feels so natural. To do that, we're going to need a totally different kind of map.
So, enter the tone nets, which literally means tone network. Think of it like a geometric map for music. And the most important rule on this map is that closeness equals similarity. Chords that share notes and sound alike, they're neighbors.
Now look at how this map is built. It's this grid where every single triangle you see represents a perfect major or minor chord. So instead of a straight line, music suddenly becomes this landscape of harmony that you can actually move through. Notes and chords that sound similar are literally right next to each other. Okay, so let's see this in action. A chord change isn't a jump anymore. It's just a step. To go from C major to C minor, you don't need to leap across the page. Nope. You just stay where you are and you move one single note, the E, down by one tiny half step to E flat. And that's it. It's the shortest possible path. This is a visual representation of efficient, elegant songwriting.
And hey, this isn't just some pretty picture. This geometric approach gives us a really powerful new way to understand the complex, emotionally rich music from composers like Wagner and Liszt, whose work, by the way, often completely defies traditional analysis.
So far, we've only talked about pitch and harmony, but music has another equally important dimension: time. And it turns out rhythm also has a deep and surprisingly simple geometric structure.
So while harmony creates these intricate, almost lattice-like shapes, the geometry of rhythm, well, it's often found in the simple perfection of a circle.
It's all about one elegant idea: distributing beats as evenly as you possibly can.
This brings us to a concept called Euclidean rhythms. Just imagine you have a certain number of beats, let's say 3, and you want to spread them out as evenly as possible over a cycle of 8 counts. Well, there's a simple, elegant algorithm that does this perfectly. And the result is a rhythm that just feels fundamentally balanced and satisfying.
And here's the amazing part. This one simple algorithm, it generates the foundational rhythms of music all over the world. That trizilio pattern, that classic 3-beat rhythm over 8 counts, it's the core of so much Latin and rock music. 5 beats over 8, that gives you the cinquillo. And Dave Brubeck's iconic Take 5, that's just 2 beats distributed over 5 counts, repeated. It's like a universal language of rhythm, and it's generated by pure geometry.
So we can see harmony as a journey through a geometric space, and we can see rhythm as the elegant distribution of points on a circle. But if we can map it all out like this, does that take away from the art? Does it somehow kill the magic?
I really don't think so. It just gives us 2 complementary languages to describe the same profound experience. One language talks about emotion, expression, and feeling. The other talks about symmetry, transformation, and structure. They're not in conflict. They're just 2 sides of the same beautiful coin.
Look, understanding the elegant mathematics behind a chord progression or a rhythm doesn't make it less moving. If anything, it does the exact opposite. It allows you to appreciate not just the emotional effect of the music, but also the breathtakingly elegant and often simple structure that produces it. It reveals the architecture behind the beauty.
And that leaves us with one final, kind of tantalizing thought. If the language of music is so deeply intertwined with the language of mathematics and geometry, the same language we use to describe the universe itself, what does that say about music's place in the world? What other deep connections are just waiting for us to discover?